Welcome to Tic-Tac-Tour. In this video, we are going to be exploring equivalent algebraic expressions with a particular focus on simplifying polynomial expressions and determining if they are equivalent or not. In order to take a look at this a little further, we're going to do a quick recap first about some key terms, including polynomials, like terms, and the degree of a polynomial and or term. Let's jump right in. All right, so firstly, a polynomial is a mathematical expression made up of one or more terms that are being added or subtracted. There are some special examples or special cases to identify. Right here we have when there's only one term, we call that a monomial. If there are two terms, like 3x plus 5, we call that a binomial. And if there are three terms, we call that a trinomial, like 3x plus 5y minus 9. The more common example of a trinomial that you must have seen if you've learned about quadratic expressions or functions by now is 2x squared plus 5x minus 9. That general format, different numbers, is the quadratic expression in standard form. So that's a very common example of trinomial. What you can't have for a polynomial is any variable with a negative exponent. If there is a negative exponent in your final answer, more likely than not, it's not a polynomial. So you must only have terms like this wherein you have positive exponents for your terms. They may have a coefficient. There may be multiple variables as part of your term, but you can't have any negative exponents. Let's take a look at what like terms are, because you're going to need to know that in order to be able to simplify these expressions. So those are any terms that have the same variables and the same exponents on those variables. So let's take an example like 5x squared y to the 3. If I have another term like 10xy and I want to add these terms together, notice that the x has an exponent of 2 here, whereas the x in our second term has an exponent of 1. Also, the y has an exponent of 3 here, and for our second term, the exponent is 1. Both the terms have the same variables, so they both have x and y in each of them, but the exponents don't match. Therefore, these are not like terms. However, if I were to adjust the second term, and you can't just adjust it, like you can't change it if you just want to, but I'm just saying that instead, if our example had been 10x squared y to the power of 3, and we were trying to add that to 5x squared y to the power of 3, then we could go ahead and add them together and get 15x squared y to the power of 3, like that. So that's the difference between like and unlike terms. Lastly, we are going to quickly recap what the degree of a term is. So in order to determine the degree of a term, we can add the exponents together. So the degree of this term would be 2 plus 3, which is 5. The coefficient doesn't have anything to do with this. You just add up the exponents of your variables. If you have a constant, like let's say the value had been just 5 itself, then the degree would be 0. Okay, so if you want to find the degree of a polynomial instead, you would find the degree of each term in your polynomial expression. So for example, we have 3x squared plus minus 2. The degree of our first term here is 2. The degree of the second term is 1. And the degree of the last term, a constant, is 0. And so the degree overall for this polynomial is 2. You always go with the term that has the highest degree. Generally, we use this to help us order terms when we're writing them. So we always write the term with the highest degree first, and then it's in descending order beyond that, just as you can see right here. Beyond this, if you are to study math further in terms of advanced functions, you will learn about functions with various degrees and how the key properties relate to each other when they have a particular degree for the polynomial overall. So that will be relevant later as well. So it's a big concept just being simplified a little bit right now for our purposes for this lesson. Okay, so now we're going to shift into simplifying these expressions. If you'd like, you can pause the video right here so that you can try this before we start taking it up. If not, then let's jump right in and get started. Alrighty, for the first example, you'll notice that the values outside of our brackets, so right here and here, are +1 in both cases. For the first case, there's nothing there, so we're implying a 1. And in the second case, there's a plus sign, but again, the 1 is implied. So really, the brackets don't serve any purpose here besides just emphasizing that you have one polynomial being added to another. So we're going to go ahead and get rid of them just because it'll make it a little bit easier to look at. Once and if you are more comfortable, you're welcome to just start adding the like terms, assuming that there is no coefficient outside the brackets and you are just adding them, then you can just go ahead and add the like terms as they are. But I think it's better practice to first get rid of the brackets by dealing with whatever coefficient there is to make sure that you don't miss that detail in case there is a coefficient, and then starting to add the like terms. In this case, once we have gotten rid of the brackets, we notice that negative x squared and 6x squared can be added together. And when you do that, you get 5x squared. Next, we have negative 4x plus x, which gives us negative 3x. And lastly, we have positive 5 being added to negative 11. And when you add those, you get negative 6. Pretty simple, right? Let's complicate it just a little bit. For question B, notice that now we have a negative sign outside of our second set of brackets. For the first one, it's just like example A, the 1 is implied, and so nothing really changes for that set of brackets. So we're going to pull out that polynomial. And for the second one, we are going to need to remember that this negative 1 needs to get distributed to each of our terms in the brackets. So we're going to go ahead and do that. When we do that, we take negative 1, multiply by the coefficient, and that's going to change the sign. So negative 1 times positive 2 is negative 2x squared. Negative 1 times positive 3 is negative 3x. And negative 1 times negative 7 is positive 7. Now we can collect the like terms just like we did before. So we have 4x squared minus 2x squared, which gives us 2x squared. Then we have 7x minus 3x, which is positive 4x. And lastly, we have negative 3 and positive 7, which is also positive 4. Okay, we have successfully simplified these two expressions. Last question. We are going to take a look at how to now determine if two expressions are equivalent or not using what we just learned and what we reviewed about polynomials, like terms, so on and so forth. So let's take a look at that question. You've been given the two functions, f of x and g of x. If you haven't been introduced to function notation as of yet, you can just assume that we are just talking about the expressions themselves and we're trying to figure out if those are equivalent, or you can understand that f of x is the same as saying y equals and follow the example that way. So for f of x, our first function here, and if we are trying to compare that to g of x over here, there are two ways that we can do this. In case we are to substitute a value into both of these functions, and for x that is, and if it so happens that when we simplify the expressions after substituting the x value, if they don't turn out to equal to one another, then and like we don't get the same value, that means that the functions are not equivalent. So even one case where the expressions are not equivalent is sufficient to prove that they don't represent the same expression overall and that they are not the same function. But if you're trying to prove something to be true, you have to prove it to be true for all possible cases. That means all possible x values. And I don't know about you, but I don't want to sit here for and show my work for all possible x values or to guess for when the case is when this doesn't work. So long story short, the best method is to go ahead and use our skills that we just practiced when we were simplifying the expressions in our previous questions. Go ahead and do something similar here, simplify both of these expressions, and then see if those final simplified expressions are the same or not for f of x and g of x. If they're not, then they are not equivalent. If they turn out to be the same, then we've proven that the expressions are equivalent for all possible x values. Okay, so let's get started. Again, if you want to pause the video here, go ahead, give this a try. Otherwise, we're going to go ahead and start simplifying these expressions. So first off, for f of x, we are going to distribute and get rid of the brackets. So the negative outside of the first set of brackets, I'm going to distribute that to everything on the inside. And that's going to cause some sign changes. The second set of brackets, there's nothing that changes because there's just a positive sign out front. And the minus 3 stays as is. Now we're going to go ahead and collect like terms. So we have negative x squared plus 3x squared, which gives us 2x squared. Negative 3x and negative 2x makes negative 5x. And lastly, 5 minus 3 is positive 2. So this is our simplified expression for f of x. Now we're going to do something similar for g of x. The first few terms, we'll just copy them down as they are, as there is no set of brackets there. The second set, notice that we have a negative sign again. So in that case, we are going to assume that this is negative 1 and multiply each coefficient by, and the constant by negative 1. In doing so, we get positive 5x squared minus 6x minus 2. And again, we're going to go ahead and collect like terms. So we have negative 3x squared and positive 5x squared, which gives us 2x squared. Next, we have positive x, negative 6x, which gives us negative 5x. And lastly, we have positive 4, and negative 2, which gives us positive 2. So let's take a look at both of our simplified expressions. Notice that the expressions match perfectly. Both f of x and g of x are equal to 2x squared minus 5x plus 2. Therefore, both of these functions are equivalent. All right, that sums up equivalent algebraic expressions when exploring polynomial expressions. I hope you found this to be helpful. If you'd like to learn about any other similar topics, please feel free to comment below and let me know. Thank you so much. Have a great day.